Hello, everybody. Today, I'm going to talk about dispersion engineering in photonic crystal fiber. My name is Majid Ibn Ali Aidari from Oceanic Engineering. Here is my Google Scholar profile. The main focus of my work is photonic integrated circuit, passive and active component design. I'm going to show you how to design and manage photonic crystal fiber. So, Oceanic headquarters is in Sunnyvale, California, and you can see the different branch of Ozen on the map. All in all, we are Ansys elite channel partners. We are consulting and selling Ansys software. As you see in this slide, Ansys software tools cover different fields. I want to focus on photonic side, and I want to focus on Lumerical, especially Lumerical MODE today. I want to design an engineered photonic crystal fiber. Then I will show you how, step by step, you can design an engineered dispersion in photonic crystal fiber. So, there are a lot of applications for Lumerical MODE. With Lumerical MODE, you can simulate photonic integrated circuit like waveguide, like taper, coupler and resonator, thermal tuning and switching, electro-optic modulator, fibers, lasers, different applications like LiDARs. So in Lumerical MODE, there are three solvers: FDE, EME, and variable FDTD. That I will describe a little about these solvers. You can simulate your waveguide. For instance, this is a waveguide, and you can see a mode that is confined to the waveguide. You can simulate your waveguide in Lumerical MODE. You can calculate group index versus wavelengths. You can calculate the dispersion. You can calculate coupling lengths, and you can calculate the overlap between two modes. So another solver in Lumerical MODE is EME. In this picture, it's eigenmode expansion, as you see in this picture. You can see the waveguide shape changing along one direction. With EME, you can calculate the mode profile at each length. You can calculate the transmission, and you can obtain mode profile, transmission, group index, effective index at different points, like this point, this point, this point. And as an example, you can see here the transmission versus length. So we have a lot of application in terms of laser design, detector design, LiDAR design, that we need our structure changing along one direction, along, for instance, this directions. So the next solver in Lumerical MODE is Variational FDTD. Sometimes you need to optimize your 3D structure. This is a time-consuming calculation. In this case, you can collapse the 3D planar with 2D effective material. As an example, for instance, here you can see that this is a 3D structure, and we want to calculate as a 2D structure. So in this case, for instance, for silicon, with the height of 200 nanometer and width of 500 nanometer with refractive index of 3.58. If you consider an effective index with 2.85 and do the 2D simulation, you will get the same result. So it's very helpful tools in the Lumerical MODE, in the Lumerical MODE software. So now we want to design a photonic crystal fiber. These are two papers of mine that I bring this picture from this paper. So yeah, as you see here, this is a photonic crystal fiber that you see some white hole on it, that it shows some hole through the silica fiber. And the blue one is silica, and the white color is air, and the yellow one is fluid. So we use a fluid injection to the first ring to engineer the dispersion. But how we select the parameter, just consider this note that the ratio between the diameter to the pitch must be smaller than this number, 0.406. In this case, you have just fundamental mode. So let's design a photonic crystal fiber using Lumerical mode. So first of all, you need to start the Lumerical mode, define a geometry, define a material, define your simulation region, and run FDE and take the result. So let's do the simulation. So you can select Ansys Lumerical Launcher. As you see here, we have a different packages like FDTD stack, FDE, EME. Just if you want to work with this solver, FDE, I will describe in my next videos regarding to these packages. But now we want to focus on FDE. So select the FDE. So here you can see the Lumerical mode windows. So first one is material. You can define your material as you wish. You can insert your material from other database. You can define a constant value. You can add any material that you want. You can define your structure here. Any shape that you want. For instance, for this case, we need a circle. And here that you can use a Lumerical component. For instance, in this example, I want to use a photonic crystal. And in this one, you can add a simulation region. For instance, for this specific case, I need FDE or eigenmode solver. So let's start. Start first with circle. We add a circle, right click on a circle. So then put edit prod objects, rename it to fiber. So, and the radius is 15 micrometer. And then for the material, I will select in the next steps. So would apply, and then you can go and select these tools to fit the windows. So as you see here, now we have a fiber. So in the next step, we want to add photonic crystal to the fiber. So you select photonic crystal here. Then I will select this one, double click on it, and you can see here, we can see some component added here. Right click on it, edit project, edit object, change, for instance, change the name to PCF. In the PCF, the radius is 0.6 micrometer, the pitch is 2, the number of rings is 6, the whole number, the H number is 2. And for the material, I select H for the air because I want to put hole on the fiber. So H and click apply and OK. So you see here, this is a photonic crystal fiber. But the first thing, we need to add other parts. We can copy it, this one, select these tools here and put it. Click on it. So then right click, I put edit object, change the name to first ring. Radius, pitch the same, but the number of rings here is 2, and the 1 rings need as I want omit 1 ring. So apply. So the same material I used at the moment, so apply and okay. So this is our first ring. So next we add the simulation region, FDE here. So click right, edit object. So we want to calculate 2D calculation and the Z normal geometry. We select 10 micrometer, 10 micrometer. So mesh setting 1515, boundary condition, select PML to absorb the light. PML, and for material, we use conformal variation 0 because we don't have metal and it doesn't matter in this item. So apply and okay. So let me check again. Boundary condition. Yeah, we forgot to put this one to PML. So apply and okay. So now we select material. In the material, you can see a different material here. We want to add a silica as a background of fiber. So I click add button. Then I scroll down and select Silmeyer. And you see here, I can change this to silica. And where is it? Where is silica? So yeah, silica. And now you can see some coefficient here, A0, B1, C1. So you can see this slide and use these numbers. And you can put this number to this table. So to save the time, I open another file that I have already insert these numbers. So as you can see, silica here, you can see that this number is related to this number that you can see in this slide. Okay. Now we go to material. We can select, we can plot the refractive index versus lambda in this window. So we select silica and change the wavelengths from 0.6 to 2 micrometer, and then plot new window. So the loss doesn't matter. If you see, the value of loss is very small. So I close it. So this is the Selmayr for silica. As you can see, the refractive index changing versus wavelengths. So now every time we must check it that the material is correct for our simulation. So now I close the window. So check the FDE. You can see geometry, mesh setting. So mesh setting, we start with 15 to see what's going on in the simulation if this number is not correct. Okay, so boundary condition, you can see here, material. So that's it. And we can run the simulation. So This is, if we want to run the simulation, we click this button, is run. So this is this check for, we can check the material that we checked recently, and so now can put the run, click the run. So in the run button, you can see this is a eigensolver analysis, EME analysis window, object, script. So we want to use this analysis and eigensolver analysis, and you can bring these windows from here. Actually, if you cannot find these windows, you can come to the view and then select Windows and then select eigensolver analysis. So in the eigensolver analysis, you see for we want to calculate mode for this wavelengths. Just we want to find a one mode because it's photonic crystal, and we are curious about fundamental mode. We don't have any band waveguide, so I select calculate mode. So we see that there is no physical mode. So we must switch to layout by this button and increase our meshing, for instance, to 100. And redo simulation. And again, no physical mode were found. So we increase the simulation, the mesh setting to 200. So it's 200. Now redo the simulation and calculate the mode. And you see a nice mode here. This is a mode 1. Effective index is 1.45. The wavelengths, you can see the loss value here, group index, and it's a T polarization. So if I increase the, so please remember this number. So if I increase the mesh setting to for instance to 800, redo the simulation for this number, we check the accuracy, we can see that. So let me so we are waiting to finish this simulation and check the number with the previous simulation. So as you can see, the effective index loss is not important. The group index is the same of previous simulation. So I think 200 is good. So for the boundary condition, because fiber is kind of symmetric profile, so we can select X mean to, for instance, to symmetric, and Y mean to asymmetric. And you see here the X mean is symmetric, the color is blue, the Y mean is asymmetric, the color is green. So if I do the simulation for this new case, you can see that the speed of simulation is much better, and the value of effective index and group index is same. So if we change also the boundary condition to, for instance, for this one to asymmetric and this one to symmetric, what's going on, what's happening? As you can see, the color changes here. So the simulation, do the simulation, calculate the mode again, and we see that the value again doesn't change. So it means that doesn't matter where you consider symmetric and where you consider asymmetric, but if you put both of them to symmetric, so you can see that now this tree region is blue. So if we run the simulation and calculate the mode again, we cannot find any physical mode. So you can do this kind of job, but always symmetric and asymmetric works. So I select XM into symmetric and YM into anti-symmetric, and it's good. So I could apply. So I run the simulation again. Now we know that our accuracy is good. We use a boundary condition, symmetric and asymmetric boundary condition. Now we calculate the mode and we see a nice mode here. Now we want to do some frequency sweep. We select the frequency sweep. We want to sweep the frequency from 0.6 to 2 micrometer. We need 20 number. Just we want to track selected mode. We don't need dispersion and band waveguide now. So I put frequency sweep. So we wait for a few seconds because we use the optimum condition of the simulation and we want to calculate the dispersion. So this is the effective index versus wavelength. So we can calculate the dispersion. In a new window, you can see that this is a dispersion versus wavelength. As you can see here, the zero dispersion is very important. So you can see that zero dispersion is around 0.87 micrometer. So now we change we fill the first ring of hole with up to fluidic. So if you see here, I defined some material like M1, M2, M3, M4, and M5. So that the M1 is 1, M2 is 1.32 or 34, M4 is 6.36, and M5, as you can see here. So for instance, if I infiltrate the first ring with for instance M5, apply, okay, you see a different color here. It means that the different refractive index, and do the simulation and calculate the mode and do the frequency sweep same as before, and frequency sweep, and I'm waiting to finish the simulation, and I'm curious that where is the zero dispersion wavelengths now. So select the dispersion, plot in new window. So as you can see here, the zero dispersion is shifted to this wavelength, 1.43, from 0.87 to 1.43. It means that the dispersion is shifted to this wavelength. And just by injecting the fluid, and the zero dispersion is shifted. And also the slope of dispersion also is quite linear. It means that the third order dispersion, or beta 3, also is constant, and beta 4 is 0, and sometimes it's good for the nonlinear application. So let's go back to another property like script file. So this is a script editor that you can write your program. For instance, for our case, this is a simple program. It's not professional, but it's simple to you understand it better. So I need, for instance, because I want to extract this result as it's the result of one of my papers. So I want to extract this graph, dispersion versus wavelength, for uninfiltrated 1, 2, 3, 4 refractive index of fluid. So we need 5 simulation to extract these 5 curves. So I select 20 because I have 20 number for each case. As you can see here in the frequency sweep, this is 20, and so for I equal 1, I smaller than n, I equal I plus plus. So first switch to layout. It means that you switch to layout and you are not in analysis mode. So let's select first string. You select first string here and then click circle. It means that select circle and then put the material with M underline number. So it means that M underline num2 string, and find modes, select mode 1, select mode 1, then track select mode 1. As you can see here, if I run the simulation here, it means that calculate mode, then yeah, track select mode 1. It means that if you click on checkbox, if you put the checkbox, it means that you track select mode to 1. Okay, then frequency sweep can get data from F, loss, and other parameter, and then you can plot a different refractive index. So I run the simulation and see the result. So I think this property of numerical mode, actually not numerical mode, but numerical, that you can write your code and you can actually do some systematic study on your structure. It's very good, and we can use of this property. So I'm waiting for the result that then we compare the result with the output of paper. So yes. So to calculate the result, again, this is a cross-sectional view of fiber. This is a 3-dimensional of fiber. This is XZ view. This is XYZ view. You can write also some command here. This is some toolbars that you can use it. Yeah. So if you see this picture, you can see that, yeah, it's calculate the dispersion versus wavelength for different refractive index of fluid, 1 for, yeah, 32, 34, 36, and you can see this curves and you can compare it with this curve that this is output of paper. So I'm very happy that actually I followed this video with you. And so how to contact us? You can contact this information as you see in this slide. And yeah, thank you. Thank you.